In lecture 9, we will go through more features of multinomial Logit model. The entire lecture will be divided into 3 shorter videos, which will be easier for you to review. In this video, we will try to check the aggregation property of the MNL model. This is a quick summary about the key assumptions and issues related to the multinomial Logit model. In the previous video, we already go through the estimation of the parameters theta applied for the MNL model. And today we will go to check the aggregation, which is equivalent to the elasticity for this model. In order to define choice elasticity of MNL model, we have to recall the demand elasticity, which we are defining in our previous lectures. EIJ here is the elasticity of the demand for the good I with respect to the price of the good J. If I equal to J, then we say that EII is the direct elasticity. If it's not, then it's called cross elasticity. Also, we have some assumptions about the model. The demand of the good I is a function of the price for all the other goods, that is P1, P2, till Pj. If the changes of the demand and changes of the price is small enough, then we can use the first order partial differentiation to define the demand elasticity. We can apply the similar definition for the choice elasticity. Here we use the symbol ENJKL to represent the elasticity of the probability of the individual n, selecting the alternative k respect to the changes in attribute j or alternative L. And this formula shows the definition of the choice elasticity. Here we will have the probability and the attribute for the I and alternative L. XJLN is the jth variable used to specify the utility of alternative L to the specific individual n. And we also have the model to represent the deterministic utility and the utility of the alternative L for the individual n is a function of a set of variables x1, x2 till xj, and for each variable xl, it contains a set of attributes which can be observed for each individual. Usually we specify that the first term in this vector is a constant, that is 0 or 1 in our definition. If the changes of the probability and the attribute is small enough, similarly we can apply the first order partial differentiation to define the choice elasticity. Now let's see how we can apply the choice elasticity for the MNL model. And this is the expression of the choice elasticity. With the MNL model, we know the expression of the probability of choosing the mode K. And we can make a slightly modification about the formula. Then we can further derive the first order partial differentiation of the probability with respect to the attribute xjl. And we will get the very complicated formula here. This formula can be applied back to the definition of the choice elasticity, and we also have the modified probability. And with this one, we can have the choice elasticity as the function of the attributes and the deterministic utility. And we can further derive this formula to some simpler format. With these 3 equations, we can get that the choice elasticity would be the function of the attribute and the probability, that is xjl times the summation of the probability q times the partial vk over partial xjl minus partial vq over partial xjl. In the definition of the choice elasticity, we assume that the utility isn't a function of a set of attributes with respect to all alternatives. But with the MNL model, we assume that the deterministic utility is just a function of the attribute with respect to the alternative L. In that sense, VL is not related to x1, x2, or xj. It's just a function of xl with the same alternative. And so we have the conclusion. Partial Vk over partial Jl is always 0 if k is not the same to L. Under this condition, we will have the simplified choice elasticity. So the first term here is always 0. And for the second term, if j is not the same to L, then it's also 0. Only when j equal to L, we will have as partial VL over partial JL, and the cross elasticity can be simplified as minus xjl times the probability of L times partial VL over partial xjl. Now let's see what's the result under the condition of k equal to L. The first step, we will expand the equation with the condition of k equal to L. So we will replace all the index L with k. And for the second term here, you will see that if q is not the same to k, then the value is always 0. If q equal to k, then we will have the value as partial vk over partial xjk. And we can also try to analyze the result for the first term. If we do the summation about the first term, you can actually take out the part here, partial vk over partial jk, outside of the summation because k is not related to q. And the summation of all the probability is always 1. Then we will have the simplified elasticity as the direct elasticity is xjk times partial vk over partial xjk times 1 minus the probability of k. This is only applied for the condition of k equal to L. And we can also recall the condition of k is different from L. And summarizing these two equations, we can write down the general elasticity function. Here we will add one dummy variable, delta KL. Delta KL equal to 1 when k equal to L, and it's 0 for the other conditions. In the MNL model, we assume that the deterministic utility VL is a function of XL, and this assumption can be applied for the choice elasticity to further simplify the expression. In our model, we assume that VL is a linear function of the attributes XL. That is, VL is theta times XL, which can be written as theta 0 plus theta 1 x1L plus theta 2 x2L plus theta p x pl. And with this linear format, we will have partial VL over partial xjl equal to theta j. And that will give us the simplified elasticity as xjl times theta j times delta kl minus the probability of L. Now let's see how we can apply the choice elasticity to get the aggregate elasticity. First, we will recall one important restriction. The expression here indicates that the percentage change in xjl is the same for all individuals. For example, if we consider the transporting mode, and if we increase the transit fare or the gas price, and this one will actually be applied for all the individuals in the transport system, which means the changes in the attribute for each individual is the same to all the others. And we also define the aggregate elasticity as EKL over J, which would be delta NK over NK over delta XJL over XJL. Here, NK is the expected number of the individuals choosing alternative K, and EKLJ is just the elasticity of the number of individuals choosing the alternative K with respect to the changes in attribute XJL. Now let's try to find out the relationship between the aggregate elasticity and the choice elasticity. First, from the definition of NK, we can find that it's just a summation of the probability taking the alternative K for all the individuals. And delta NK would be a summation of delta probability K. And then the aggregate elasticity can be rewritten in this equation. We can further modify the equation in the next several steps. And then we will try to apply the restriction for the changes in the attribute for individuals and the whole population. And in this equation, you will find that the term here is just the choice elasticity that we derived previously. In that sense, we can see that the aggregate elasticity is just the weighted choice elasticity for all individuals. For now, we have already solved the first two issues, estimation of parameters and aggregation. Then we can move to the third one, independence from irrelevant alternatives property. Now let's try to solve the third issue about the INA property. From the MNL model, we know that probability of taking the alternative I is represented by this formula. And then we can find out the ratio of taking the alternative I and K, which will be exponential Vi over exponential Vk. We find that this ratio is not related to any alternatives other than I and K. This property can be used to determine the infamous red bus and blue bus problem. Suppose that if we have two transforming mode, car and bus, in one transforming system, the deterministic utility for car and bus are the same. They are all capital V. Then we can find out probability of taking car, which is 1/2, and the bus is also 1/2. But if we paint half of the bus blue and the other half as red, you will find that there will be three alternatives: car, red bus, and blue bus. And obviously, the utility for red bus and blue bus are still the same, and is also the same to the car, which are all capital V. Then we can apply the MNL model to find out probability of taking each mode. The probability of car is 1/3, red bus 1/3, blue bus is also 1/3. And summarizing this result, we can find that probability of taking bus becomes 2/3, and taking car is 1/3. And this result is obviously different from the previous one, and it's actually counterintuitive. It's actually impossible for us to change the probability of taking the bus and the car just by changing the colors of the buses. The reason for this problem is like the estimation actually violates the key assumption 3 for the MNL model. The assumption assumes that the random components is an independently identical distribution. In this case, for the number distribution, we should assume that the car, red bus, and blue bus, all the random terms are independent to each other. So they will have the covariance of psi as this. But in reality, for the red bus and blue bus example, the red bus and blue bus are highly correlated to each other. So these two coefficients are different to each other. And of course, red bus and blue bus are some extreme case. But the bus versus express bus versus rail, or bus versus carpool, or the QW plus 403 versus 403 from Toronto to Hamilton are some general case. The MNL model cannot deal with these scenarios, so we will go to check some other measures, such as the multinomial probability model and net Logit model. We will cover these two models in the rest of this class.